Okay, let's start with something you already know. The effective focal length, EFL, of a lens is a special length given by the distance between the rear principal plane and the focal plane, or the image plane, for an object at infinity. That you know, right? And it's easy to get a lens design program to output that number. Just get it to output the number, right? But how do you measure it? Okay, the bottom here illustrates one way to do it, or one way it's done in some factories. In fact, this is the way it's done in the factory that I used to work in. And it's also one of two ways discussed in Joe Geary's book. All right. So you've got a collimating lens and a target, a small target placed behind a one focal length away from the collimating lens. It should be small because you want it to subtend a small angle so that the image formed is free from distortion. Right. So you put the lens under test in front of the collimator from the image, and with the known angle of the off-axis ray and the known measured height of the image, you can use trigonometry to determine the EFL. Okay, but under manufacturing conditions, your lens elements are not necessarily all centered. They could be slightly decentered and tilted. Because in a lot of lens systems in mass production, nobody aligns each element to each element. They just drop everything in, tighten the retainer, and ship, right? So the question now becomes, how do these centers and tilts impact the measurement of the EFL? And also, does that impact the EFL reported by your lens design program? Let's find out. One way to do it is to simulate the measurement in a Monte Carlo tolerancing analysis, right? You can model a collimator. This is a paraxial thin lens model. This is a small object subtending an angle 1 degrees to this datum plane here, which is represents the front mechanical housing of this lens. The lens under test is a double Gauss with 50 millimeter nominal EFL. And I'll measure this height h prime here. By the way, I'll get back to this measurement in a minute because here I'm measuring the height of a point spread function, which has its nuances. Anyway, what I do then is I take the measured image height h prime divided by the nominal image height, which is known, and times the nominal EFL, which is also known. This is scaling the EFL to get the measured EFL. Okay, this is one way to do it. All right, so what happens? What do we get? Okay, so I have 1,000 Monte Carlo samples, and each sample I optimize the off-axis focus of the point spread function. That's important. And these are the tolerances given to the lens elements. You can pause the video to have a look if you want to examine that. And I have got two plots, two histograms of 1,000 Monte Carlo samples. The top plot here is a plot of EFL of each lens using the Zmax operand EFLY, which, by the way, is not affected or unaffected by tilts and decenters. Okay. The bottom plot here is a histogram of the same sample of lenses from the Monte Carlo run. EFL is measured using the simulation I showed here. Okay. So what do we notice? The bottom plot has a noticeable wider spread. In other words, the measurement technique has added variance because of the tilts and decenters, right? It does. So, so what does this mean? What does it mean? It means that a whole bunch of conversations have to take place when you do a tolerancing analysis and when you design a lens. You've got to think about how it's measured because that could add variance. You got to talk to the technician. You got to talk to the manufacturing engineer. You got to talk to the customers. A whole bunch of conversations should take place or not. I don't know. You decide whether or not it's important for you, right? Because here, all I'm doing is I'm just having some fun simulating this thing and well, potentially opening up a can of worms. Anyway, till next time. Bye bye.